So we talked about resource extraction when there's a finite resource or finite stock of the resource underground. A common question then for resources like oil or natural gas or anything in which there's a finite stock of it is, will we run out of it? And in particular, will we run out of oil? Because oil is an energy commodity, and this class is about energy. So let's talk about whether or not we will run out of oil. When will we run out of oil if we do? Proven world oil reserves are about 667 billion barrels. World oil production is 63 million barrels per day. That's quite a lot. Assuming no change to production, how many years until there's no oil left? 29. So 29 years. One thing I should note, though, is that these figures, these numbers that I presented on the previous slide, they were taken from 1980. The proven oil reserves in 1980 and the production and consumption of 1980. So did the world use the last of its oil in 2009? Clearly not. So what happened? Proven oil reserves at the end of 2014 were 1.7 trillion barrels, quite a lot more. World oil consumption in 2014 was 92.1 million barrels per day, or 33.6 billion barrels per year. Proven reserves today are equivalent to 50.6 years of current world oil consumption. So if everything stays the same, we find no more oil under the ground and demand stays the same over the next 50 years, then we'll run out in 50 years. But will we? What are reserves? Reserves are the portion of energy resources that is estimated to be both technically and economically feasible to produce in the future. Reserves are not a geological constant. We're not talking about simply the actual stock of the resource underground, the physical quantity of the resource underground. We're talking about something that's a function of engineering and economics. What's economically feasible and what's physically practical? What are we actually capable of pulling out of the ground? Proven reserves, the portion of energy resource that is estimated with probability greater than 90% to be both technically and economically feasible to produce at current prices and using existing technology. So proven reserves is that definition of the stuff that's technically and economically feasible to produce. Proven reserves can change. If prices rise, proven reserves will increase to include resources that could not have been economically produced at lower prices. For example, offshore drilling or fracking. As prices of oil go up, so imagine this, a stock of oil goes down, the current stock of oil, and so the scarcity rent's going to increase and the price of oil is going to increase because we think we have less oil underground than we do. All of a sudden the prices are going up. What's that going to do? That's going to incentivize companies to come in and extract more expensive oil, or it's going to incentivize them to invest in technologies that allow us to extract oil that wasn't otherwise extractable, like fracking. Only proven reserves can be considered an asset under U.S. accounting rules. Mexico switched to this definition of proven reserves in 1998. Creating a large adjustment in reported reserves. You can see that in the graph to the right. So you can see how proven reserves can change just by changing the definition of what proven reserves are. Here's a table of estimated world proven oil reserves in different countries. You can see that it's been increasing over time across the globe. In 1990 it was 1 trillion barrels. 2000 it was 1.2 or 1.3 trillion, and 2014 is 1.7 trillion. You can see the distribution of how those proven reserves have changed across the globe, across regions. Here's a change in world oil reserves from 1980 to 2014. So this is the proven oil reserves have been increasing over this time period. Here's the change in reserve production ratio from 1980 to 2014. In other words, how long in years we expect our proven reserves to last. And this has been increasing over time. So in 1980, we thought the reserves were going to last 30 years or 29 years as we saw. We're up to roughly 55 years. And so our time frame for when our oil is going to run out just keeps increasing. So why are world oil reserves changing? We have continuous technological change in the exploration, extraction, and recovery of oil and other fossil fuels. For example, we have offshore drilling. In 1891, there was the first drilling in a lake from a wooden pier. In 1933, we had the first mobile offshore drilling, Lake Pellereau in Louisiana. 1947, the first bottom-supported platform. That's 1 mile off the Louisiana coast and 30 feet of water. 1979, we had the first rig exceeding 1,000 feet of water on the continental slope. At this point, the current technological frontier, with prices of oil as they are now, the largest or the most impressive oil field is the Tupi oil field in Brazil, discovered in 2006. It's 160 miles off the coast of Brazil, below 1.2 miles of ocean, and then 3 miles of salt and rock. So that's the length at which we are willing to go to get oil at current prices. So you can see as prices increase, that technological frontier is going to expand. We're going to go into harder and harder places to get oil. At some point we might go to space for resources, not oil, because oil doesn't exist in space. The key takeaway: the total mineral in the earth is an irrelevant, non-binding constraint. If expected finding and development costs exceed the expected net revenues, investments dry up and the industry disappears. So if costs are larger than revenues, people won't extract the resource. Whatever's left in the ground is unknown, probably unknowable, but surely unimportant, a geological fact of no economic interest, according to Michael Alderman, an energy economist. So what do the future supplies of oil look like? There's large geological sources of hydrocarbons that may one day be economically worthwhile to extract, like oil sands. There's a lot of this in Canada. Estimated total resources is approximately 3.5 trillion barrels. Current concerns are about the environmental effects of the extraction process, and so if we internalize those externalities, the cost of producing oil sands is going to increase substantially. Right now, they're not really economically feasible anyways, and so we don't see a lot of oil sands extraction. We do see oil shale extraction, though. This is fracking. It's estimated total resources approximately 4.8 trillion barrels in the United States. There's a lot of fracking potential around the globe. Technologically feasible to extract oil from shale, but most wells need an oil price of at least $50 per barrel to be economically feasible. So you'll see fracking dry up when the price of oil goes below 50 barrels. How will technology for these and other resources change over the next 40 to 100 years? Well, it's impossible to predict, but if prices of oil keep rising, then we'll probably see new investments in more difficult places of extraction. What about peak oil? What is peak oil? Peak oil, or calling the point of time at which world oil production is at its all-time maximum. There was a guy named M.K. Hubbert predicted it in 1956 that oil production in the United States would reach its peak in the late 1960s or early 1970s. Was he proven correct? We'll see in a moment. The model of oil production over time that he developed is known as the Hubbert's curve. Many attempts to apply this model to global oil production. So there's people still attempting to predict the peak in oil production across the globe. So here's a graph from roughly 1915 through 2020 of U.S. oil field production. So M.K. Hubbert said we'd see a peak in oil production in about 1960 or 1970. He was right for a while until around 2010 when fracking came into play. And we see a large increase in U.S. oil production after 2010 due to fracking. So this is a technological change that allowed an increase in oil production of oil that was otherwise not accessible. So peak oil takeaways in 2015, U.S. oil production was 6 times higher than Hubbert had estimated. Hubbert ignored technological progress and price. Why was he wrong? He got a few things wrong. So he ignored technological progress and price. As economists, we should be worried about ignoring price. Assume that there was an accurate estimate of ultimately recoverable resources. In other words, he thought we knew what was underground, and insisted the price did not matter and that economics was irrelevant. The updated predictions of the world peak are always just around the corner. So the takeaway here is don't worry about it. Economics will take care of it. We may see a peak. In fact, we may have already seen the peak, but it's not because of the geological constraints. It's not because we have a finite resource and we're running out of it. It's because economics is taking care of it. The prices are rising. We're going to find substitutes for our uses of oil, like electric vehicles.